Even all research scholars I shared, sir. Actually, research scholars we have in a group.
No, I think they are the people who should basically be a part of this.
Yeah.
Because
And
they are the
also
engineers
the
for tomorrow.
fellow members of ACC. I am also a group member.
Acha, okay. Because they are the engineers for tomorrow.
Sanat Kumar worked, we both worked, he is there from 10 years, Nagarjuna.
Wow.
He is my right hand for online.
Ajay, Mr. Sanat Kumar worked for Nagarjuna Construction?
Yes, sir. The college is backed up by Nagarjuna Construction.
Okay.
Sharp fork Shurman, sir.
Uh-huh.
Sir, actually interaction we can allow at the end, sir.
Whatever you feel. I think people, if they want to,
mute and unmute, it will disturb your lecture. That's the reason.
I know. Then I think let it be a discussion
you
at the
take
last.
1 hour at least minimum. Then we'll go for interaction. If the content is there, you can go up to one and a half hour. Actually, we made 2 hours slot for the speakers. You can go for up to 1:30. So 1.5 hours you can take. No issue.
Yeah.
I will start, Sanat.
Yeah, let's do.
Sanat, you can. Good afternoon, one all present here. I'm happy and honored to welcome all the participants for this 4th phase online Masters Trainers Training Program. So it is a part of upskilling, or you can say reskilling program for construction engineers, especially those who are working in the Nirmiti Kendra. We have submitted a proposal to Ministry of Skill, they approved, and 3 phases successfully completed. We have planned for 52 days programs. They told you conduct 13 days offline, online, offline, online. Now we come to the last phase of the upskilling program. I'll thank the director and ministry officials for approving our proposal and permission given to conduct upskilling program. So as all the engineers must know that there are a lot of changes with respect to the technology and also use of materials, how to make a concrete with highly durable concrete with aggressive environments. See, a lot of infrastructural developments are going on in India. You have seen what is the money spent by the government of India and state governments. And because there is a big opportunity for engineers to learn how to make a high-grade concrete, high-strength concrete, high-performance concrete. So actually the concrete we have used 20 years back only concrete. Now the concrete is performance-based concrete. Today with us our speaker, Honorable Speaker Engineer Siddappa Hasbi sir, a lot of experience with Silica Fume. I'm happy to share that they supported, when sir was in Elcom, they supported my research. I did my research in PhD College of Technology with the Silica Fume high performance concrete of 60 megapascal. Application part is Kaiga 2 plant. I'll thank you once again, Siddappa sir. And also my association with the speaker is almost 25 years. We are working in the same area of interest. I'm happy and honored to welcome today's speaker of the day, Engineer Siddappa Hasbi sir. Thank you very much, sir, for accepting our invitation and sparing your valuable time to share some of the material, new generation material, or you can take high performance material as one of the ingredient of the concrete to perform according to the requirement. Thank you once again on behalf of our skill center and on behalf of all the participants. I welcome you once again, sir. And also welcome all the participants, our Nirmiti Kendra engineers, project directors, and also I welcome Engineer Ashok, the CEO of the company, the Construction Management Training Institute, a leading training institute in Bangalore. Thank you all, Vidya, for supporting and showing some of our students to interest to take part in this. And also I will thank, welcome Sanat Kumar. He is the backbone of online program. So always he is supporting, is our well-wisher. So last year, sir, just for the information of the speaker, we conducted 42 online programs during the COVID situation, sir.
Wow.
Last year, for the benefit of all the engineering community, including the engineers.
Yeah.
Before going to this one, just a brief introduction about the speaker of the day. See, Engineer Siddappa A. Hasbi is a metallurgical engineer, graduated from Karnataka Regional Engineering College. Now it is called as NITK and Suratkal. He started his career as a production engineer at Indian Metals and Ferroalloy Limits and was associated with the company for 2 years. Since then, over the past 32 years, he has been associated with the product development and technical marketing and sale of silica fume. It is also called the microsilica to the concrete applications, refractory, oil well, and fiber cement industries in India and the other SAARC countries. There are 7 countries, I think I'm right.
Yeah.
He is presently working as a managing director of the European-owned multinational company Corniche India Private Limited, heading their business activities in India and the SAARC countries, plus the Middle East and the Southeast Asian countries. He is a regular contributor with his papers to the ACI Concrete magazine and the Concrete International UK magazine and the various construction-related magazines in India. I'm very happy and honored to welcome once again Siddappa ji, sir. And now I request you to take over the session. And also I request the participants, you can post your questions in the chat box and we'll take the questions only at the end of the lecture because we don't want to disturb the speaker of the day. Then I request all the participants to please follow the protocols. Please mute all your videos only. Thank you once again to all of you. Now I request him to take over the session.
Yeah, thanks a lot, Venkatesh Babu sir, for the introduction. Let's start now. I think I work as Venkatesh Babu sir said, Corniche India Private Limited. We are located in Navi, Mumbai, Maharashtra. The title, what I thought was most appropriate would be use of silica fume. That is normally in short form it's called SF in high performance concrete, HPC. Silica fume is a mineral additive or a mineral admixture. And what is a mineral additive? It's a product which enhances the performance of the concrete. And various mineral additives are listed here. It's a fly ash, ground granulated blast furnace slag, silica fume. We have the rice husk ash also. A lot of research work is going on. Maybe I think in a decade, probably next 5-10 years, you'll have rice husk ash also in the market to be used in concrete. And the last one is metakaolin. It is basically calcine from the kaolin deposits. Normally, why do we need the high performance? Why high performance? That's a novel question people ask. Why do we need these new concretes? Why do we need these high strengths? And why do we need this low permeability in the concrete? And my answer to them is, we need durability. You can see this flyover. It's in one of the North African countries. Can anyone guess the age of the flyover? It's less than 15 years. 15. You can
only
see,
50,
I think
only 50, sir. Okay.
Only 15.
Okay.
You can see the analysis made revealed that the soil was rich with sulfates. So it's thoroughly a sulfate attack to concrete. And you can see this reinforcement. It's almost looking like an external reinforcement. So this flyover did not last for 15 years. It was scrapped and it was rebuilt with silica fume concrete in 1990. So 32, 33 years on, still it's running. Just 6 months ago, I think my friend Robert Lewis was driving on this flyover. He said, Hasbi, everything is intact. So that's durability for you. And the second good example, what I can give on durability is the Kinzua Dam in the US. This dam was built originally in 1967. It came for repairs in 1975-76, first repair. This was a condition of the dam. You can see the still in basics.
The energy dissipating system, I think, the energy dissipating system.
Yes, completely it is basically abraded. And wise heads in the US thought that the aggregates were not good. Local aggregates were very soft. So they decided to import the neighboring good aggregates from the neighborhood, and they did the repair work. And that also did not work much, basically. I'll take further in detail. I'll take that case study. But in the meanwhile, I always believe in law of fives in the concrete. Any structure, it starts from the drawing board, designing, and ultimate to the damage. Normally, I think people are fussy about spending initially. Say, I have put it, 1 rupee spent in phase A, that is design and construction. If you are not doing a good concreting job, you'll be spending 5 rupees in the initiation and 25 rupees in propagation. And ultimately, repairs are very, very expensive. You'll spend 125 rupees. Instead, I would always suggest to people, don't be stingy, spend 2 rupees in place of 1 rupee. You will save your 125 rupees. Repairs are always expensive. Build the structure to last long initially in the first stage itself. Then coming to the product itself, what's in the name of my product? Condensed silica fume, as it's called. We are condensing the hot smoke around 180 to 200 degree hot smoke coming out of the chimney. We are condensing it, cooling it. That's how it's called, a condensed silica fume. The shortened version is a silica fume. That's an industrial name also. Since it's in submicrons, normally people refer to it as microsilica. The size of the microsilica grains is 0.15 microns. It's an extremely small material. And it is not silica flour or a silica dust. And it is not micronized silica. These are nothing but the ground quartz powder, which is crystalline in nature. And our silica fume is amorphous in nature. Fumed silica, precipitated silica, gel silica, and colloidal silica. These are the silicas also in the market, but they go for different applications. They go to the rubber industry, pharmaceutical industries. Coming to development of silica fume concrete, it's not a new product. We have a good history. It goes back to 1947. Samples of silica fumes were collected from the chimney from the plant, first time. And in 1952, samples of silica fume concrete have been buried in acidic sulfate-rich soil in the outskirts of Oslo, Norway. Still, durability studies are going on. And it's almost 80 years old now. The concrete is still standing. That's durability for you. And 1970s, filtering system and concrete trials first started in Canada. And 1976, the first standard for the silica fume use in concrete came out from Norway. And I've also listed the major silica fume concrete production startups in various countries. You'll see Canada started in 1980, 81 was Iceland, US 82, Japan 83, UK and the Middle East 85. India, the first project which used silica fume concrete, was specified in 1987. Eventually, the project started consuming it in 1990-91. It's for a fertilizer plant, Deepak Fertilizers, very close to my place now here, in the outskirts, in MIDC, Taloja. It was used in the construction of drilling towers. I'll show you the details in my subsequent slides. And you'll see China started later than us, but China is many-fold bigger silica fume user in their infrastructure than India, because their infrastructure growth is quite big and there is a lot of silica fume production in China. India doesn't produce any silica fume because of the power cost. That currently, there are over 12 standards or codes of practices. ASTM C1240 is the most accepted standard the world over. I put XX because look for the latest one. The latest available on stands is 2015. ASTM C1240-2015. And we have the IS standard also. I am a part of the IS committee for silica fume. We started discussing in the mid-90s, 1995. And finally, we were able to come out with a standard 8 years later, 2003. And we have a revision now, 2017. That's the latest one. No modifications, no changes there, same as 2003. And we have the Canadian standard and the European standard, which was finally formalized in 2005. So in India, the Indian construction industry refer either to IS or ASTM. So silica fume is used in the construction of world's largest projects. As per our market guesstimates, over 10 million cubic meter of concrete per year, silica fume concrete is produced. It's used in the construction of bridges, roads and tunnels, hydraulic structures, skyscrapers, and hazardous environments, like for durability, purely for durability purpose. And the standards I will just summarize. You can see the standard comparison. The first is the ASTM, what you have. The next is the European, and the fourth one is the IS, Indian. Everywhere what you see is it has a minimum SiO2 content requirement, which is 85%. Silica fume should contain 85% amorphous silicon dioxide. And also you see there are limits for loss on ignition. Loss on ignition, though ASTM is a bit on the leaner side, I think we talk about not more than 4%. And moisture content has to be less than 2%. Bulk density, we have to report. Bulk density, undensified material, we call the bulk density between 180 up to 500, 550. And the densified material will be between 550 to 700. And the pozzolanic activity index, it has to be 105% minimum. And the 45 microns retained wet sieving, it has to be 10% max. Basically, silica fume. If you have a pure silica fume, it will be 0 because everything passes through the 45 microns. It is 0.15 microns in size. And next slide, I'll show you a few more things. Yes, this is a part of the IS 456 what I have taken, where I think mineral admixtures, it comes under mineral admixtures, fly ash, silica fume, what I showed you, rice husk ash, metakaolin. So silica fume production, I'll just touch it briefly. My first 2 years, I have operated a plant. I operated a silicon and ferrosilicon plant, and basically I have been involved in production of silica fume. Silica fume is produced by the collection and treatment of the fumes released during production of high-grade ferrosilicon and silicon metal. This is one of our industrial sector area in China. Till mid-95, this was what it looks like. There are 15 plants in that industry. You can see this polluted area. Post-95, when we started collecting silica fume, this is what my plant looks like. Atmosphere is very clean. We are catching the dollars which were flying in the air as pollutants. This is one of the plant in Bhutan producing ferrosilicon where we collect the silica fume. A tiny country like Bhutan, where the power is very cheap, they produce silicon and ferrosilicon, so we produce silica fume. Production, I'll just stress raw materials, quartzite, and the black materials, carbon in various forms, coal, coke, charcoal, wood chips. We are basically smelting in a furnace. The smelting is melting and reduction. That's how it's called smelting. Reduction happens at high temperature between 1950 and 2000 degrees inside the furnace. It's a hot pot running under 5-bar pressure. So basically, I think it's a two-phase reduction. Quartzite, SiO2, crystalline material, it gets reduced to SiO, and SiO further gets reduced to Si. So that metal which is produced, Si, in case of ferrosilicon, iron filings are there, so FeSi, it's tapped out periodically from the bottom of the furnace. But not all SiO gets converted, reduced to Si. Part of the SiO, because it's an open top furnace, comes in contact with atmospheric oxygen. It gets oxidized to silicon dioxide again. That is silica fume for you, which is amorphous in nature, which would have gone out as a pollutant into the atmosphere. We are trapping it. We are condensing it. And we are running through a pre-collector and pre-fan where all the impurities are segregated, gravity-wise. And pure fumes are run through the baghouse filters. The bags which are used in this pollution cleaning system are extremely fine cotton bags. There is a company called Gore-Tex in the US. They supply these bags. They are branded bags, and the guarantee what they give on these bags is less than 5 ppm. The air which goes out after the collection of fume is less than 5 ppm. That is cleaner than the air what we breathe. So all the fumes are collected to the, they get stuck to the bags. It's a reverse air cleaning principle where the bags get inflated and deflated. So when it's inflated, enough powder gets stuck to the bags. When it gets deflated, the powder collapses. It falls into the chain conveyor and we are collecting the fume here. Though as produced material is undensified in nature, density will be something like 180 to 250, 260 itself. So roughly a 25 kg silica fume bag, undensified, will be between 2 and 3 times the size of a 50 kg cement bag. It is that voluminous. So handling, to improve the handling and to improve the transport, we started densifying the material. We pneumatically densify the material to bring the density between 550 to 700, so that the bags transportation becomes easy for us. It doesn't occupy more volume. As said, production quartzite, wood chips, coal, coke, charcoal. It's the open end of the furnace where smelting happens. And this basically is one of our Norwegian plant, and this is our Bhutan plant producing ferrosilicon. And what happens inside this furnace at 5 bar, between 1950 and 2000 degrees? As I said, yes, quartzite and carbon. Two-phase reduction, SiO2 gets reduced to SiO, and SiO further gets reduced to metallic silicon. Silicon is tapped out periodically from the bottom, from the tap hole, and part of the SiO comes in contact with atmospheric oxygen to form SiO2 that goes out through the chimney, which we are trapping it, collecting it, running through the baghouse filter, and collecting the fumes. So some of the shots from the plant where the hot metal is poured on the bed, what we call, we make it as a cake and then further crush, break it into lumps. So raw materials, quartzite and black material, we have carbon electrodes, and this silicon and ferrosilicon production requires a lot of energy. India is rich with all the raw materials, but energy is very expensive in India. That's how we are not producing any silicon metal in India. Had we been producing silicon metal in India, we could have produced locally the silica. We are importing the silica fume. Lot of energy. To produce 1 ton of silicon metal, we need 15,000 units of power. And to produce 1 ton of ferrosilicon, we need 9,000 units of power. And industrial power today in India is not less than 6 rupees a unit, which is very, very expensive. As compared to Norway or China and Malaysia now and South Africa, where the power cost there is something like 1 rupee 25 paise to 150 paise only per unit. So smelting, silicon metal and ferrosilicon production, we get a co-product called silica fume. So silicon metal on the left side to you, and this is silica fume, the powder on the right side. So how does the silica fume look like under the scanning electron microscope? Perfect spheres, very, very fine material, 0.15 microns in diameter. It's finer than the cigarette smoke. The cigarette smokers will tell what the particle size of the smoke. It is small, but silica fume is finer than the cigarette smoke. So silica fume is a product of the silicon alloy industry. It's a glassy microspheres, 0.15 microns in diameter. It's a pozzolana. It reacts with calcium hydroxide to give you this calcium silicate hydrate gel. And it is anywhere between 85 to 98% amorphous reactive silicon dioxide. So forms of silica fume, as I told you, as produced material is undensified material. The density is between 150 to 350 kilos per meter cube. The densified version, we pneumatically densify the material to bring it between basically 500 to 700, 550 to 700 kg per meter cube. And some countries, use of silica fume is mandatory. A country like Poland, for example, the aggregates are very reactive there. So it's a norm that silica fume has to be used in every kilo of cement what they use. So in such countries, basically, we supply the silica fume in the pellet form, and they produce silica fume blended cements there. It is ground during the cement production itself, like how we are doing the fly ash and the GGBS blended cements here. I think they do silica fume blended cement in Poland, for example. And the next is the slurrified version. Slurry is very common in Europe and US. Slurry is nothing but 50% powder and 50% water. Basically, I think they use slurry to ensure dispersion of the fume is proper. But today, the type of high-end mixers what we have, dispersion should not be an issue with even with the powder. And also, I think for us in India, importing slurry would be very expensive because we have to pay a lot of transportation cost and import duty to water also, because slurry is 50% water and 50% powder. So it will not be viable for us. So forms of silica fume, on the left-hand side, you see the first one is a densified form, the middle one is undensified form, and the last one is a slurry. Properties of silica fume, it is amorphous in nature. I stress on the word amorphous. When I say amorphous, it is safe to breathe in and breathe out. It's safe to use. It is not a health hazard. But crystalline material is a health hazard. It causes crystallosis. It's a form of a cancer, actually. It's a material, crystalline material is angular in nature. When you are breathing in, it goes and gets stuck in your lungs. You cannot breathe it out. And the color ranges from light to dark gray. And the particle shape, they are perfect spherical particles. And particle size, as I said, average diameter is 0.15 microns. This is approximately 80 to 100 times finer than the cement grain. And specific surface area, it will be in the range of 15,000 to 30,000 meters square per kg. Can you guess how far it can spread? I'll give you an example. The quantity of silica fume required to fill in the football, I think you may be soccer fans, that football, that quantity can be spread over the entire football ground. It occupies that much amount of area. So comparison of silica fume, fly ash, GGBS, and OPC. I have tried just to show you people how silica fume differs from the rest of the three products. It's highly siliceous. The other three products fall between 20 and 50%. Our material is 85% plus, typically 90% and above. And second, on the fineness, your specific surface area. The other three products fall between 300 to 700, whereas a silica fume is minimum 15,000 to 25,000 meters square per kg. Portland cement, GGBS, silica fume, and fly ash. That's how they look like physically. And when I say silica fume is 100 times finer than cement particle, what do I mean? If you put these materials under scanning electron microscope, this is a part of your cement grain. The entire cement grain cannot be seen in the scanning electron microscope. And this will be my silica fume. It's a very, very fine material. It's 100 times finer than the cement particle. How does it work? Basically, these are the two cement grains, actually. In between the two cement grains, you will have several thousand silica fume particles flooded together. And it basically has physical properties and the chemical properties. Physically, it fills in all the pores of your concrete. It refines the pore structure of your concrete. The pores get smaller and smaller. The concrete gets denser and denser. And chemically, it gets involved only in the secondary hydration when there is enough of calcium hydroxide leached out. The primary hydration happens with cement and water. There's a lot of calcium hydroxide leached out. That's basically the white stuff, what you're seeing along the corners of the cement grain. The silica reacts with this calcium hydroxide to give this calcium silicate hydrate gel. This will be a conventional concrete without silica fume. You can see this lot of white stuff, calcium hydroxide. It's a useless stuff with a lot of pores in the concrete. Add 8 to 10% of silica fume to this concrete. This is what the structure will say. There is a total refinement in the structure. The silica fume fills all the pores in the concrete. The pores start getting smaller and smaller. And in the secondary hydration process, it reacts with calcium hydroxide to give this calcium silicate hydrate a good bond. So cement hydration has schematically shown how it works. Along with cement hydration, the other pozzolanic reaction. This is the cement, C3S and C2S. When you mix it with water, there is a hydration. You get this calcium silicate hydrate binder, which gives some strength in your ordinary concrete. When you, and some calcium hydroxide is liberated, as I said. This is a cement hydration process, stepwise. And when you introduce silica fume, SiO2, what it does with water, basically, it generates a lot of calcium silicate hydrate. It consumes all this calcium hydroxide. So the amount of calcium silicate hydrate available is more. As a result, the strength will be more. This is what the silica fume does. This I just put it schematically to show you process-wise. This is a pozzolanic reaction. This is cement hydration. This is a pozzolanic reaction. So fresh concrete properties, it makes the concrete cohesive. The concrete does not segregate. It is non-segregating. It makes the concrete adhesive. And the concrete, silica fume concrete does not bleed. No bleed water. And all put together, it makes it thixotropic. So this results in improved pumping. It can be pumped to long distances, higher heights without any segregation. And it's effectively used in shotcrete applications where the rebound is almost nil. Whatever you spray to the wall, it sticks. And self-compacting concrete, I think it has become very popular in the last 15 years or so. You don't need any vibration to the concrete. It flows on its own. And underwater placements. Silica fume concrete has been extensively used to pump underwater in dams and hydraulic projects. There will be no washout. When I say cohesive, you can see the stiff silica fume concrete sitting on the dumper there. And when it hits the concrete, it gets the energy. And silica fume being spherical, it gives a ball bearing effect to the concrete. It starts flowing. Non-segregating, you can see this 280 mm plus clump in one of the activities. The formwork is not all that good here. You can see this. There are hollowness in the and also there's water standing on the floor. The silica fume concrete, you see how stiff it is sitting. Nothing is bleeding out, and the water which is standing on the floor, it's not getting mixed with the concrete. Nothing gets into the concrete in the silica fume concrete. And whatever is in the concrete, nothing gets out there. It can be pumped to various distances, various heights, no segregation. And as I said, shotcrete, you see this gentleman spraying. He is not wearing any protection there. Had it been an ordinary concrete, the aggregates would have come back on his face. The rebound will be more there. Whatever you spray, it sticks. The rebound is bare minimum. Bleeding, you can see this conventional concrete on the left side, what I have schematically shown. You'll see the bleed water on the top. But silica fume, that is absent. There is no bleed water. It's a very cohesive concrete. And underwater placements, it's one of this thing. You can see this environmentalist standing on the right side there to check whether the concrete pollutes the water. But there was absolutely no pollution. The concrete did not bleed. It did not get washed away. Placing, compacting, finishing, curing. It has to be done systematically. The water cement ratio, what you use in silica fume concrete, will be very less. So the surface tends to dry off almost immediately. So start curing the material immediately after placing the concrete. And no shortcuts. 28 days wet curing is a compulsion, like what you do in your conventional or ordinary concrete. So silica fume concrete does not bleed. It must be cured properly to prevent drying out, especially in hot environment like ours, hot weather environment. Mist spraying, bonding, membrane coating, wet hosing, shading, all, no rocket science here. Common practices what are already being followed. Minimum 7 days wet curing. Ideally, it has to be cured for all 28 days. So hardened concrete properties, the silica fume concrete is strong. It's high strength. The permeability is very less, very low permeability. Both put together, it's highly durable. Durability against abrasion and erosion, durability to chemical attack, durability to water, chlorides, sulfate, and alkali silica reaction. Alkali silica reaction is the reactive aggregates what we have. We eat our Himalayas, we have this reactive ASR problem. So it doesn't allow the aggregates to expand and crack the concrete. It binds the aggregate and keeps the concrete stable. So high strength concrete definition is a relative term. So today I think I can easily tell concrete starting from 60 megapascal. There are countries which are producing 150 megapascal concrete. Yes, in India, we have reached up to 100 now, 120 megapascals. So with these silica fume high strength or concrete, we can design structures with increased heights. There are towers which are 1 mile high up in the air. We can have thinner columns and floor buildings, thinner bridge decks, longer bridge spans, and increased resistance to physical damage. These are all the advantages what you can get with silica fume concrete. So about the shot rate with silica fume, it substantially improves the adhesion and cohesion properties of the shot rate. We are able to single spray or a single layer up to 400 to 500 mm thick. We can build with a single spray, which is not possible with your ordinary concrete. Ordinary concrete, probably even up to if you 60 to 80 mm spraying, the concrete starts falling back on its own by gravity. But silica fume concrete does not. It sticks. Silica fume concrete binds the system together. And we are able to spray on the surface with flushing water or in a tidal zone also. There will be no washout. And there will be substantial decrease in rebound, thus leading to significant saving of the concrete. Whatever rebound concrete is a useless concrete, you cannot use it. So the rebound will be very, very less with silica fume concrete. Just to show you, with OPC, you can just build maybe 60 to 80 mm thickness in one spray. But with silica fume, yes, go beyond 500 mm, single spray. You can see this gentleman how he is doing the shot rating. He is not afraid. The concrete, what he has put, it's almost, I think, 150, 200 mm thick. He's not afraid that it will fall back on him. Silica fume is holding the concrete together. It doesn't allow to fall back. It is adhesive and cohesive. So shot rate with respect to rebound, these are the actual numbers what we got from during the project in Mumbai-Pune Expressway. The overhead with the conventional concrete, the rebound losses were as high as 55 to 60%. When we introduced silica fume shot rate, SFR, steel fiber reinforced silica fume concrete, it was less than 10%. I think probably we hit up to 7% only. So there is a lot of saving, and the quality of concrete what you spray, it sticks to the wall. Here, the quality of concrete is very poor because the aggregates fall back and only the paste sticks to the wall. And on the side walls, the rebound was as high as up to 30%, basically 28 to 30%. With silica fume shot rate, it was less than 5%, maybe I think 3-4% only. And silica fume based abrasion resistant concrete for hydraulics, such as the first slide what I showed for durability, Kinjua Dam. I'll take this project a bit in detail. Kinjua Dam sealing basin repairs. This dam was constructed in 1967. Come 1975, this was the state of the dam. The sealing basin had been completely eroded. The think American, basically Army Corps of Engineers or American think tank, the conclusion what they made initially was the aggregates what they used, local aggregates were very poor there, soft and poor. So they decided to repair the sealing basin using good hard aggregates imported from the neighborhood. And they did that probably in 76, 77. Come 1985, this was the state of the concrete. Within 6 to 7 years, the repaired portion had completely got ruptured off. The concrete was eaten away. And the penetration, you can see it had gone into the original concrete also, abrasion penetration. That is when the Army Corps of Engineers and the technical heads or the research people put their hands together and they concluded, do not use fiber reinforced concrete. Use the lowest practical water cement ratio and use the hardest available aggregates. And this conclusion and the continuous efforts
resulted in using the silica fume concrete. And they did a lot of work, trials before putting it to, before laying the concrete. You can see the lab tests or abrasion at Kinzua. Steel fiber reinforced concrete with a Kinzua ore they did, and conventional concrete with soft aggregates, conventional concrete with the hard aggregates from the neighborhood, silica fume concrete with hard aggregates, and silica fume concrete with soft aggregates. These are the permutation combinations they tried. And they laid down the lab results. It was basically, it's a 72-hour test where the samples are put to hydraulic abrasion in running water, which are pelted with steel pebbles, percolated. You can see this particular thing. Silica fume concrete is flattening off there. No much wear and tear. But the ordinary concrete was giving away. Finally, the specifications, what they got out was compressive strength, 86 megapascals, and cement, they put a max, not more than 415 kgs. And for the first time, they were using in 1985 the silica fume, minimum 15%. As a salesman, I'd be very happy to sell more silica fume, but that much quantity is not required now. Today, we are operating between 5 and 8% in any of the structures. And the water binder ratio is say in 1985-86, 0.3% only. This was a concrete. And this is a sample which I took for abrasion testing, a cylindrical sample, 28 days cured. And this is a abrasion test apparatus actually. They use the steel pedal running at 1100 RPM. And you have the steel balls of various diameters pounding the concrete for 72 hours. And every 12 hours, they were taking out the sample and noting down the weight loss. That's how they put the graph, graph what it saw. And ultimately, the concrete mixed design, what they arrived at, to be relayed in 1985 was cement 386 kgs per cubic meter, silica fume 70 kgs. It's almost 20% what they use. Water binder ratio was 0.28 and slump 250 mm. The results what they achieved, in 7 days, they were able to get close to 70 megapascals. In 28 days, it was 95. And in 90 days, more than 100 megapascal concrete. After relaying in 1985, the drive immediately, because after 1 year, they had seen that particular, by the divers, they had inspected it. And then after that, they inspected it only after 12 years. And these were the inspection reports. Random cracking throughout the basin floor, minor deterioration of the baffles, and minor deterioration at the toe of the dam. Absolutely, it was as it is, very minimum abrasion. And no debris were noted in the basin, no new spalling and significant deterioration of the baffles. Erosion at the toe of the dam has not increased in depth or length. Because immediately after 1 year, 85 they had laid, 86 they had seen, after 86 they have seen 12 years afterwards. It was still standing. And the latest, I think they have still not documented, as far as I know, they have done inspection in 2018. No abrasion still, it's standing. We are talking about almost already 36, 37 years. It is still standing. Where they used to, where they have repaired, in earlier cases, they have repaired in 4 or 5 years, twice. This is the Kinzua Dam. This is a picture clicked by me when I was there in 2016. It's operating. Another good example, what I can give is the Los Angeles river channels. They used to repair these river channels every year because of the heavy erosion, because of the silt. A lot of silt, water carries a lot of silt there. You see the condition? Every year they used to repair it. They ended up with basically, I think, around 350 kg cement and around 7-8% silica fume. This is standing since 1986, no wear and tear. They used to repair it every year, 35 years now, no repairs. And placing concrete in a tidal zone in hydraulic abrasion. This is one of the cases in UK.
where the part is heavy ships. Because of the movement of the heavy ships back and forth, there is a lot of wear and tear. You can see this particular thing, a reinforcement standing up. Every season they used to repair it. And it's extent of abuse, concrete abuse here. 1985, they have laid silica fume concrete there. This was a inspection what they have done in 2015, after 30 years. You can still see their tampings are still on. The concrete is still standing. No wear and tear. Those are from Europe and US. And in India, we are not far. We applied this particular rule for two of the biggest hydroelectric power projects. One in Bhutan, that is Tala Hydroelectric Power Project. It's a 1,080 megawatt plant. And for us in Uttarakhand, Tehri, which is 2,850 megawatt plant. These are the trials or the tests what we have done with local aggregates and local materials. Only the silica fume is the imported stuff here. So we produce 4 grades of concrete, M30 conventional grade, M50, 60 and 70 with 10% silica fume in this concrete. See the specially developed horizontal shaft mixers. It's a very efficient mixer. Silica fume concrete. You can see it standing up there. Closer view. No segregation and things are bubbling. Mixing sequence I have put just for the people who want to work with silica fume in the lab. Add silica fume as early as possible in your concrete. So it's added along with the coarse aggregates. Then you are adding your fine aggregates, part of your water, then the remaining fine aggregates. Then you are introducing cement, part of the super plasticizer, remaining 50% of water along with the super plasticizer. That's the sequence what we do in the lab. And typically you're mixing it for 6 to 7 minutes to really get a good concrete mix. And in the lab, you have the flexibility to do that. When it comes to site, sequence of addition, coarse aggregates, fine aggregates, silica fume. Always add silica fume first. And ensure silica fume is there in the system before cement or super plasticizer is there in the system. Because silica fume, the densified material, it has to disperse. When it comes in contact with the aggregate, it gets crushed and dispersion starts, the physical dispersion. And subsequently with super plasticizer coming in, complete dispersion will be happening. The mixes what were carried out for this Tehri, I think you can see M30, we just use around 320 kgs of cement. And M50, M60, M70, 340, 365, 380 kgs of cement per cubic meter. We have used 10% silica fume there. And water binder ratio, you see, conventional concrete is 0.45. And silica fume concrete, we are operating between 0.35 to 0.3. And see the strength difference here. Conventional concrete, 28 days, we got 35. And with silica fume, it's between 55 to 75. And for Tala, there basically they were using slag cement. So it's a ternary blend. PSC and silica fume. And results are not bad. Similar results like Tehri. You can see the M70. Water binder ratio was as low as 0.24 only. Same abrasion testing equipment we have used to test these samples. And some of the things what the dimensions, and you have steel balls of various sizes, basically which keep pounding the concrete to basically create that abrasion sort of what we have heard from the CWC, Central Water Commission, the actual velocity of water encountered in any dam in India is between 45 to 60 meters per second, which is very high. And with the 1100 RPM, what we are doing this test, if you convert that into the velocity, it's hardly 17 meters per second. So we had to upgrade this particular 1100 RPM speed to 3 times, to 3360 RPM, to bring it to a realistic velocity of water incurred by Indian dams, which will be around 50 to 53. And we have done all the testings with 3360 RPM. And abrasion loss, M30, strength losses, you see, 6.26%. Conventional concrete. whereas with silica fume concrete, it's between 2.5 and 3. The numbers are not showing you much difference, but I'll show you the graph what I'm putting, and I'll show the condition of the sample upon testing, how it looks like. In fact, I think this is 72 hours testing cycle. Out of curiosity, we went beyond also. We did it twice to 144 hours. Our silica fume concrete was flat. Abrasion was flat. No severe abrasion, we were saying. But the conventional concrete was giving away almost. For Tala, similar thing. This is a 28 days cured sample before putting it to testing. And after 72 hours of testing, the conventional concrete, you can see this, how badly it has been abused by abrasion. Closer look, you can see there are cracks, pits, and some of the aggregates have come out because of poor bonding. We had collected the leftover slurry at the bottom just to see what all has come out after wear and tear. See, these aggregates had peeled out because of poor bonding in the conventional concrete. With respect to silica, we just schematically put it, how it looks like. With respect to M70 concrete, after 72 hours, this thing, you can see this. Surface is smooth, only the watery top layer has gone out. The aggregates are sitting intact. And the residue, what we had collected, closer look, the bonding looks good. No cracks. Only the watery surface we could collect. There was no peeling of aggregates because the bond was very good. Silica fume was giving a cohesiveness to the concrete. There was no aggregates peeling out because of poor bonding. Schematically, we have put it. Observations: a use of silica fume has helped in reducing the loss due to abrasion erosion up to 40% and above as against the original concrete. The cracks around the aggregates in conventional concrete indicate that further dislodgement of aggregate is possible if the tests were continued. And a good bond between the aggregates was seen in concrete with silica fume, indicating the narrowing of the curves as the test is further continued. And high strength alone is not a criteria for abrasion erosion resistance concrete, but good bonding between aggregates is a must, which is possible only with the addition of silica fume. So lessons learned: use of silica fume concrete helps in attaining higher strengths and ensures better bond, better aggregates, making the concrete highly resistant to abrasion and erosion. This improved durability makes high strength, high performance silica fume concrete most suitable for use in hydraulic structures. And if triple blend or a ternary blend, what we call, which is the OPC, silica fume and GGBS, or OPC, silica fume and fly ash is used, then this not only improves the durability and the economics, but it also helps the environment. More like a green concrete. So conclusion: high strength silica fume concrete does work as anticipated in situation of high exposure to abrasion erosion forces. Coming to high strength concrete and high performance concrete in India now. It has been used in the construction of nuclear power projects, hydroelectric power projects, used in the construction of roads, bridges and tunnels, in the high-rise structures, repairs and rehabilitation projects, and hazardous environment for durability purpose. That's the first project what I spoke about, Deepak Fertilizers in 1987. I'll show you, this is the Prilling Tower of the Deepak Fertilizers, where basically they're cooking the raw materials to produce the fertilizers. The raw materials used are chemically very aggressive, and acid is also part of the raw material. So the concrete has to withstand acid attack and the chemical attack. It's a 78-meter height, 18-meter diameter, 9-meter diameter at the top, 18 at the bottom. Approximately 1,500 cubic meter of, they designed it for M35, but basically they were looking for durability. This was built in 1990-91. And basically, this was a picture which was taken probably sometime in 2009, 2010. After 20 years, it is still standing, no repairs. It's highly durable. It's still working. So nuclear power structures, it all started globally in CO in France, they had used in the construction one of the small nuclear power plants on the dome, basically. They used a 12,000 cubic meter. Based on the use and success there, I think the NPC people took their advice and guidance, and they have used silica fume concrete in the construction of Kaiga 1 and 2 and Kota 3 and 4. Basically, this was used sometime during 97, 98. They have used it only on the domes, 2,000 cubic meter each. And based on the success what they did there, subsequently 2 years later, Tarapur 3 and 4, the entire reactor building of both the reactors is done with silica fume concrete. Just from 2,000 cubic meter, it went up to 120,000 cubic meter of silica fume concrete. And today it's being extensively used in nuclear waste handling system also to minimize radiations. With silica fume concrete, even the radiations will not leak out. So requirements were the pressure containment vessel should satisfy structural integrity, leak tightness, serviceability, and durability. High performance concrete with silica fume was found to cater these requirements. The compressive strength, what they were looking was 60 megapascal. Basically, 60 was not important for them. The split tensile strength, they wanted minimum of 3.87 or 3.9 sort of a thing. To attain this 3.9, they ended up making an M60 concrete. And water permeability, you see, as per the DIN 1048, the limit is 30 mm. But here they just gave us 5 mm. That means it's an absolute watertight concrete. And the workability slump, they had around 175 plus or minus 25. And the water binder ratio, 0.32. Structures at Tarapur, 3 and 4 with silica fume. The reactor containment structure, M60, around 52,000 cubic meter concrete, which had wrap, inner containment wall, and inner containment dome. And they have this Calendria vault, basically to prevent this radiation shielding. They use heavy density concrete. They use hematite ore as an aggregate. And the density of the concrete there is 3.9 to 4, as against your regular concretes, which are 2.2, 2.3 sort of a thing. And in the intake structure, it was M40. They wanted it to be watertight concrete. And in the pump house, M40, 25,000 cubic meter concrete. That was a breakup in Tarapur. And look also, I think, how the mixed designs are improving each passing day. In Kega, in 96, 97, to produce an M60 concrete, they had used 475 kgs of cement and around 7.5% of silica fume with water binder ratio of 0.32. And 2 years, 3 years later, the same concrete was produced by reducing 50 kilos of cement. From 475, they came down to 425, 7.5% silica fume there. And water binder ratio again, maintaining the same. This is a Kega during construction, the dome. You can see the dense reinforcement. They wanted the concrete to be free flowing. They did not want any honeycombing. They wanted concrete to cover all parts of the structure. Silica fume concrete was a solution for them. 3 and 4 domes in operation now. Tarapur. These basically are 210 megapascal, 210 MVA domes, whereas MW, so megawatt domes. This is 540, more than double for Tarapur. See the dense reinforcement during construction. This is the Calendria vault what I was talking. The concrete almost looks like brown because they use hematite ore as aggregate. So advantages of using high performance and high strength concrete at Tarapur. Entire primary containment structure of Tarapur 3 and 4 have been designed using high strength, high performance concrete of M60. This resulted in economy, reduced heat of vibration because they could reduce 1 bag of cement per cubic meter. The heat of hydration was less and enhanced performance requirements. I think you could go back to the library. See this issue, September 1999. It's on Nuclear Power Special, Indian Concrete Journal. There's a lot of good information. And coming to hydropower projects, we are the world leaders. We have number of hydropower projects using Silica Fume concrete. Salal Dam, that's where it started in 1992. Salal Dam, incidentally for you, geographically, it's very close to India-Pakistan border. I was there, carrying out trials on the spillway. Every year, they used to repair the spillway in the off-season. In 1992, we just put a meter by meter Silica Fume concrete, and likewise, they put meter by meter high-strength concrete, conventional concrete, and steel reinforced concrete. These were the 4 or 5 types. And when we went back the next year, 1993, to see, all other concretes had got washed away. Only Silica Fume concrete was standing. That's when NHPC decided to repair the entire spillway with Silica Fume concrete. And NHPC, based on this particular success, they started specifying Silica Fume concrete for all their new projects. Tulasi was the first new project in Jammu and Kashmir, which used Silica Fume for the entire dam structure and even the short reading of the tunnels. See the mixed design, sir. Then they used 500 kilos of cement to produce an M60 and 7.5% Silica Fume. An interesting thing is you will see this precipitated silica they used because still they were not doubly sure that Silica Fume concrete will be a waterproof, which will not bleed. So that's how they had used this 0.5% to ensure that concrete doesn't bleed. And for all subsequent projects, they knocked out this precipitated silica because precipitated silica is an expensive material and that is not required basically. Silica Fume does the work. You can see the water point ratio, 0.34. Come to Sri Shailam Dam. This was the biggest repair work which has been done in any of the Indian dams till today. They pumped 2,500 cubic meter concrete underwater because the whole dam was hanging. Because the back current and abrasion, the concrete had washed off. They pumped 2,500 cubic meter of concrete and countless gallons of slurry or grouting. They have grouted it very well with Silica Fume concrete. This repair has been done in 1999-2000. I think more than 20 years now, standing. No repairs have been done and no repair works have been taken up after that. For the Tala project, the head race, Tala is a 1,080 megawatt plant with total tunnel length up to 28.5 kilometers. This is the head race tunnel. And the SFRS, basically it was the M30, grade of SFRS concrete what they use. And the mixes, what they have used here, M30, M50, M60, and M70. And apart from abrasion, we have measured the RCPT coulombs also. Conventional concrete, you can see this water permeability was as high as 90 mm. Introduction of Silica Fume, it was traces, 2 mm and less. And also the RCPT, what you see here, 2,600 coulombs, it was less than 1,000 coulombs with Silica Fume concrete. And the abrasion numbers, what I had shown you earlier, it has been tabulated. Pictures at various stages of construction. The spillway bucket. Concrete dam is 92 meters height and 130 meters in length. Basically in operation, 1,080. Come to the next big project, Terry, 2,350 megawatts. You can see the size of the structure. Huh? You can see this dumpers and trucks. They look like miniatures. Now the mixers, they use M40, M50, and M60. And basically, I think these are the results what they have got. Summary. And coming to Alta Dam in Norway, the reason why I take this particular thing is this dam, basically they use silica fume to control the heat of hydration. You can see the mixes what they have used there. They just added 10% of silica, 10 kgs of silica fume, basically to control bring down the cement content and lower the heat of hydration. Only 100 kg cement, 10%, 10 kg silica fume for an M30 concrete. 135,000 cubic meter concrete. So silica fume concrete has been used even for seismic retrofit, Little Rock Dam in California. So a bit what they have done. Cement 405 kgs, 10% of silica fume. Some steel fibers they have used, 15%. Water cement ratio 0.45. And slump, I think probably around 80 to 100. 28 days, they were hitting more than 50 megapascal. Coming to the third, Hackney hydropower in Norway. It's a 60 megawatt plant. Head raise tunnel 6.5 kilometers, tail raise 675 meters, elevation, tunnel cross sections. Then they use steel fiber reinforced shotcrete. Coming to buildings and commercial structures. Very close to your place in Whitefield. Satyasai Sai Super Specialty Hospital done by L&T. All the domes, I think there are 12 domes there. It's done with silica fume concrete there. Based on the results what they got from KEGA, L&T people implied that particular technology to this project also. M35 concrete, 380 kg cement, around 8% silica fume. See the water binder ratio, just 0.3. Then ferrocement cells with silica fume. It's a Ramakrishna Mandir in Pune. The entire mandir with ferrocement cells is done with silica fume ferrocement cells. The mixes, they have been able to get 66 megapascal there. See the sleekness of the ferrocement cells. Then the stupa in the US, Colorado. They have designed it for 500 years. Entire temple structure is done with silica fume concrete. Come to the silica for the high-rise structures. One of the very few projects we started in Bombay, in the western suburbs of Bombay, Raheja people, they did M60 columns. And look at the mix: 425 kilo cement, 40 kg silica fume, water binder ratio 0.28. You see, the 7 days they were able to get more than 50 megapascal concrete. And in 28 days, it's 72. It's a M60 concrete. Parliament Library building, again, Larsen Tubro people have done this project with silica fume concrete, the entire project. Come to Bombay again, the case of Solitaires. It's one of the high rises which use M75 grade for the columns. It's basically a 32-story tower. For the first 16-storied height, the columns were of M75 grade. And come 18th onwards, it is M60 grade. And it's a 3-tier basement. The entire basement, they pumped around 5,500 cubic meter of self-compacting. OPC 400 is self-compacting, M40 grade self-compacting, 400 kgs, fly ash 170 kgs, and silica fume 20. The results what they were getting, more than 50 megapascal concrete. And RCPT, both less than 650 coulombs. Highly durable concrete. And for the columns M75, 475 kg cement, 80 kg fly ash, 50 kg silica fume. The 28 days results, you are getting, say, 85 and above. And less than 400 coulombs RCP. Ellora Fiesta is the next one, again, a combination M75 and M45. The M40, what they used for floors or the slabs, 385 kg cement, 96 fly ash, 25 kg silica. They were able to get 48 megapascal. M75, for the columns what they have used, 83 megapascal is the strength. What they General Motor, actually they built a factory in Pune. It's a car building factory. Their requirement was, they came up to us sometime in probably January, after post-Christmas. The French people were there. By the end of the January, they were sitting and they said, before monsoons arrive, which is June, we want the construction, the concrete part of the entire building to be over. So early strength development was a criteria there. So we did probably a good business by selling them maybe I think around 550, 600 tons of silica fume in just 3 months. The entire factory is done with silica fume concrete. 500 kg cement, 10% silica fume. In 24 hours, they were getting 26, and in 2 days, more than 40 megapascal. The requirement was in 2 days, they wanted the strength to be more than 35 minimum. So, then coming to roads and bridges, my very favorite Mumbai-Pune Expressway. This is first of the 6 tunnels when you start from Mumbai, the Bhartat tunnel. Short treating done with SFRS, steel fiber reinforced short treating. 475 kg cement, around 6.5-7% silica fume there. Marked with the second tunnel, and Kamset 1 and 2 are the 2 tunnels closer to the Pune. The last 2 tunnels from Mumbai, first 2 tunnels from Pune side, post Lonavala. Kamset 2, I think they have used semi-dry or a dry short treat, not a wet short treat. So it was 1.5 kilometer tunnel. And silica fume concrete has paid well there too. JJ flyover project, basically it's in South Mumbai, a snake-like structure built in one of the busiest market areas, Mamadali Road in South Mumbai. And during the day, the entire market used to be buzz and busy. So the precast elements were laid only during the night when the crowd was little less. Bombay never sleeps. Even the night crowd will be there. So length, it's almost 2 kilometers. 4-lane carriageway, 56 spans, aesthetics piers, concrete grade M75. They use silica fume 10% by the weight of cement. See the slender and sleek structure there. Casting yard, 22, probably it was around 24,000 cubic meter concrete, M75. The M75 concrete, mean target strength, what they achieved in 28 days was 81. Probably, I think even last 6 months ago, I think they are still testing the strength of the concrete. I think it is crossed now, I think 108 or it's close to 110 megapascal. Because a lot of cement was used, still the reaction is still on. See the water bind ratio, 0.29 rather. Crash barriers, the reason why I've taken this picture, you can see this grease, which is in patches, stuck to the mold. The concrete doesn't absorb anything. The grease is just looking up. Nothing gets into your concrete. Concrete is highly impermeable. During the erection, it's in operation today. Beautiful structure. See the slender sleek structure and see the space what it gives to the people. Snake-like structure. At night, it looks even more beautiful. Coming to second Narmada Bridge, done by Larsen Tubro. They have used silica fume concrete. This was done sometime in middle of 95. It's about 25, 25, 27 years old now. And I'm showing this particular picture because this is the first bridge actually, the neighboring. This picture, I think it's not, probably it was taken some 5-6 years ago, say 2015 or something, 20 years after its construction. It looks new even today. And this is an old bridge which is there, and see the condition of that bridge and the new bridge. The age difference between these two bridges is hardly 10 to 12. This is older by 10, 12 years. This looks, even after 20 years, it looks brand new. 25 years. Mixed design, what they've used, 490 kg cement, 7.5% silica fume, 0.3 water cement ratio. Coming to Delhi Metro, that's our favorite project. Delhi Metro phase 2 onwards, silica fume is being used extensively. And all the metros have specified silica fume all through on pan-India basis. Look at the mixes done, 475 kg cement, 35 kg silica fume. M60, I think they were able to hit 74, 75 megapascal. And today, the same quality concrete, they are able to produce with 380 kg cement, around 32 kg of silica fume. Probably they are using 80 to 100 kg of GGB, ternary blend. Coming to the LNG project, a ternary blend in Gujarat, it was M55 grade of concrete for pre-stress element, approximately 6,000 cubic meter concrete. Ternary blend, OPC, GGBS, silica fume. Use of silica fume, basically it was for higher lift and development. And it has been used in M35 grade concretes as well, wet joints. M55, 265, 200 kg OPC, 265 GGBS. GGBS is almost 60% there. And they have used on 7 to 8% silica fume, 0.29 water bond ratio. This is the LNG storage tanks. They use it construction of these tanks. Come to one of my favorite projects, which I was involved thoroughly, Bandra-Worli Ceiling project. Length of the bridge is 5.6 kilometers. It's a cable stayed bridge. More than 250,000 cubic meter of silica fume concrete. M50 for piles and M60 grade for HPC for piers and precast structures with silica fume slurry. This is an aerial view. I was there on the barge, the first trial barge, which was taken deep in the Arabian Sea. The first pile was poured. I think if I remember correctly, it was in 2000. And the date was October 19th. The barge. Look at the mixes, huh? M50 grade concrete for the piles and for pile cap M60 and also for the superstructures. The water binder ratio 0.27 for pile cap and pile superstructures. .27 and 0.26. M50 for piles, M60, pile caps, segments, and PS. Always build the structures to last. This is the Ocean Bridge connecting Denmark and Sweden. The designer has guaranteed this bridge for 100 years, life. 70 years maintenance free. That's the confidence of the design. The entire bridge is done with silica fume concrete. The next, closer to us, the Chingma Bridge, connecting the island to the new airport. 125 years, guaranteed life. First 70 years maintenance free. We are not far away. We are with Bandra-Worli Ceiling project. It's already 20 years standing. It's working beautifully. I have been involved in getting out this silica fume special issue. This was in October 2000. Please have a look at that. It has beautiful papers, international papers as well. 6 beautifully printed papers. I've been, as I said, I have been publishing articles in Concrete International and ACI, and also this thing. This was the first one what we did actually to bring India onto the global map. So high strength concrete, high performance concrete in hydropower projects. It all started with the Kinjua Dam, and we are the leaders today. Napta Jakti. These are two examples I've written, but there are a number of hydropower projects which are using Silica Fume concrete. And HPC in India, it all started with nuclear power projects, Kega, JJ Flyover, Bandra Worli, and we have many more to offer now. So advantages of using high strength concrete, high performance concrete, high compressive strength, high split tensile strength, faster construction, low permeability, all put together high durability. So development. How do you define development? It's a relative term. In 12 months' time, the latest development in electronics will be out of date. I think in 12 months' time, when it comes to concrete, in 12 months' time, the latest development in concrete will still be the latest development in concrete. We are learning every day, and learning never stops in concrete. Every day, every new day, new surprises, new improvements you'll see in concrete. And high strength concrete, high performance concrete, it's all about team effort. No shirking the responsibilities. All the people dealing with the project have to put their heads and hands together to produce this wonderful concrete. Thank you. These are my contacts. And you could know. I hope I have not bored you.
Yeah. Thank you, Siddappa sir. You have given a beautiful outlook and also the global and local picture about the application of Silica Fume. I think one flyover in Bangalore from Sirsi flyover also they used, what I know.
Sirsi flyover has used
70 megapascal from Mysore Road. It is also
Mysore Road.
When I saw this flyover, immediately I got it is a Bangalore.
Flyover, yeah. Same, incidentally, is the same consultant, Srinivasan, dark consultant.
Look is same actually.
A dark consultant.
Okay. Yeah. Thank you very much, sir, for your.
And I want to play that. I want to play before we go for discussions. I want to play that video also.
Sanat Kumar, Mr. Sanat.
I am there, sir. 1 minute.
You should play the video. It's a video is about the self-compacting concrete. I was a part of that particular international project demonstration. It was done in 1997 in Iceland.
Sanat, video.
Audio is not running.
The audio is.
Probably, I think Sanatji, he can share that with all the people later on.
Yeah, we can share the group.
Individually, yeah. But this, I think, it's not a big video. It's just 1.5 minutes.
What is the grade of concrete, sir? 10?
It was M60.
M60.
See the cohesiveness. I think it's a beautiful flow. The aggregates are setting up.
Global concrete.
Yeah, self-compacting concrete. And basically, we showed the demonstration to show it is working against gravity. You will see now. There is no segregation there. You see the beautiful concrete coming out there.
Oh.
Against the gravity.
Okay.
It is because of silica fume and the PC waste that makes it.
Super.
Yeah. Okay, that's it. And that can be shared with all the participants, Sanaj.
Yeah, we'll do so. We'll do.
It has with this voice recording also. So.
So now I request any questions from the participants, because there are a lot of applications that are rightly mentioned, abrasion resistance. I request all Nirmiti Kendra engineers, wherever you want to design some structures, you think of silica fume, because highly resistance against abrasion and erosion, because you are in the construction of barrages and some of the any floors, industrial floors like that. So all the floors should be resistance against abrasion and erosion, because these are the two actions make concrete to deteriorate. It is called physical deterioration. So whenever you're using a small percentage of silica fume, even a low grade of concrete, actually sir has presented even 30 MPa concrete.
Yep.
If you use silica fume, definitely the metal looks differently against with abrasion resistance and the erosion resistance. Therefore, you can think of doing only a GGBS and silica fly ash. See, this highly durable concrete. Even many projects, it is already, especially the hydraulic structures, road projects. You can say all the infrastructural projects. Here shared also, some of the buildings are constructed because the dead weight on the foundation also less. The element size is coming less. If you use silica fume with high strength concrete, all these things. So now, any questions from engineers? Anyone? You can just mute yourself. Sir, the director sir is there?
Yes, sir. Yes, sir. Good evening, sir.
Good evening, sir. Sir,
Good evening, sir.
Siddappa sir is
Good
there.
evening, sir.
Your video is closed, sir. Hello.
Yes, sir. Yes, sir. Tell me, sir.
Sir, actually, the Siddappa sir is the today's speaker. I think you are there. Any questions from your experiences? Click off.
Yeah, now we are able to. Hi, sir. Good evening.
Good evening. Good evening, sir.
He is the director of the skill center, sir.
That, sir, you are from Hubli.
Yeah, I am from Hubli, sir.
Sir, I am from Kustagi.
Acha, Kustagi.
Yes, sir.
Okay. The world is small. The world is small.
World is small.
Yeah, because Hubli, but I did my engineering from Surathkal, KREC.
Okay, sir. Which year, sir?
85 to 89.
85 to 89.
Yeah.
Good, sir. Nice.
Yeah.
Any questions from other? Hello? I am audible? Sir, I have one question.
Yeah.
So actually, if I use a small percentage of silica fume, what is the increase in cost? Because everybody thinking that adding silica fume is like a gold in concrete. Because
Yeah, no, I think, let me come. I think a lot of people, especially in Bombay, I did not touch that particular thing.
Yeah.
When you said about M30,
Ah.
in Bombay, I think with this consultant, we don't define the quality of concrete with the grades.
Yeah.
We call it as a performance.
Performance. Okay. Okay.
So I'll give you the mix also straight away.
Ah.
Basically, I think they are using 325 to 350 kg cement,
Okay.
OPC, around 80 to 90 kgs of GGBS, and between 12 and 15 kilos of my silica.
Okay.
And if you compare the cost there, it is at par now.
Yeah.
Because whatever conventional concrete you produce,
Yeah.
and this particular concrete will not cost you more than 4,500 rupees per cubic meter.
Okay.
If you produce.
But performance is a high value.
Yes, high value. And what results are you getting?
Yeah.
Water permeability, you are hitting less than 5 mm only, 2 mm and less. And RCPT, because we are in Bombay coastal side, it is less than 500 coulombs.
Okay.
And last is the strength, what we measure. And strength, we are hitting between 55 to 60 megapascal.
Okay.
Means basically what we did was, with the 350 kgs of cement, the quantity of calcium hydroxide which has been leached out, we have added proportionately only 12 to 15 kilos of silica fume to consume all that particular calcium hydroxide.
Okay.
So as a salesman, if I ask you to use 30 kgs, maybe 15 kgs will consume all this, and another remaining 15 kgs will act just as a filler.
Okay.
And that's a very expensive filler.
Yes, sir.
Yeah. So we have effectively utilized all the raw materials.
Yeah.
And
if you take the life cycle cost, I think this is highly.
Yes, life cycle cost definitely it stands. Yeah.
Performance and life cycle cost.
Yeah. Repairs are always expensive, very expensive.
Yes, sir. Yes, sir. And also this can be used as a repair material also, sir.
Yeah, in repair material. A lot of people are using it in the pre-bagged repair mixes also, in grouts and things.
Okay. Okay.
Even in plasters in Bombay, they are using it.
Yeah. So I'm happy to share that what sir has presented Kaya to, sponsored by them only, when sir was in Welcome India Limited Silka. Actually, they given me 10 bags of it as a reached PhD College of Technology. I did 60 megapascal of plant Kaiga 2 only, the dome construction only. They asked me to do HPC mixed proportioning with the ASTM durability studies from 60 to 100 megapascal. And also I did a small pilot studies at the Kaiga plant also, sir. Because they are not accepted our results, what I did in the laboratory. Finally, they told you come and do the same mix here. Then we'll see the performance. Then only we will accept your research project because it is a funded project.
Okay.
It is a very good materials. I enjoyed it. Only thing is the what you clearly shown a mixing sequence and mixture plays very important. We cannot use silica fume for ordinary drum mixtures.
Yeah.
It will not give good results. Only the RMC concrete we can suggest. So anybody who using in RMC the silica fume anywhere?
No, they are using, sir, because I think whatever on their own they will not use, but the client or customer demands they have to use.
What you have shown buildings is RMC only, everything I think.
Yeah, no, in fact, I think I'll come back to RMC. It's a bit political now. RMC people, if I'm an RMC man, you are this thing. I'll sit with you to negotiate. I'll tell, you are telling me to use silica fume, you are telling me to use PCE based admixture. So my cost will not be less than 10,000 rupees per cubic meter.
Okay.
So then you agree and you pay me 10,000. But I'll show my naughtiness there. I take 10,000, but I'll still supply you concrete without using silica fume. I'm cheating you.
Yeah.
So there to minimize that, actually, what in the last 10 years we did with
only it will work out in captive plants in the site itself.
Captive plants, and what we did was with the consultant, we asked all the builders to buy their own plants. And today the RMC business is down. All the people have their own plants, and they are producing good quality.
Yeah, you are right, sir. Any more questions? Surendra Patil, Raichur?
To share, sir.
Yes, sir.
Good news as far as the Nirmiti movement is concerned in Karnataka. Today, Honorable Prime Minister inaugurated our IT upgradation project. IT upgradation project handled by Nirmiti Kendra across the state, sir. It's a 220 crore rupees project and completed in recorded time of just 6.5 months.
Okay.
Yes.
Congratulations, sir. Happy news.
Yeah, that's a good news, sir. Yeah.
Surendra Patil, Namrata. Any questions from Nirmiti Kendra engineers? But actually, they are not experiencing first only silica fume. They are used to GGBS and fly ash more.
GGBS and fly ash.
Yeah. We have the blended cement also. Why in India still we are not getting a triple blended? What you shown in presentation?
No, in fact, I think that's this is silica fume. Basically, being an expensive thing, it doesn't become viable to blend it in during cement production itself.
Okay. It is a plan is there, sir?
Better, I think. Like blended cement, what we get in the market.
Yeah.
Yes. Basically, I think, as I told you, one instance, Poland. They use Poland is a country where they use silica fume blended cement. Because the aggregates are very reactive.
Sir, is it possible blending at site?
Yeah.
While mixing?
That's what we are doing now, sir. We are adding externally and blending it. Yes.
Okay.
Because basically, I think all these big projects now, they have an independent silo for silica fume. So you have silo for cement, silo for GGBS or fly ash, and silica fume silos.
10% by weight of cement, sir?
10 gone are the days now. I think probably up to 6% you can.
As per the mixed design, they will do, sir.
It's the based on requirement. It's the based on concrete.
Based on the requirement. Abrasion, basically, to get a good bond and this thing, you need like a couple of percentage more.
Right.
And even on the concrete roads now, I think there are a lot of potholes can be repaired with the silica fume concrete.
Sir, all high performance flows.
What is market price, sir? What is market price? Market price?
For the silica fume will cost you something for ex-Bombay. It will cost you something in the range of 28 to 30 rupees a kilo.
28?
28 to 30 rupees a kilo per kilo.
Okay.
Taxation extra, the GST is extra, and then transportation based on where it has to go, it's extra.
Okay. So I have one more question, sir. Because you told India is not able to produce silica fume, it is totally imported. A lot of ferro-silicon alloy industries are there, even Rajahmundry, Palghat, so many places. What they are doing actually now? How they?
No, in fact, sir, actually, the number of ferro-silicon plants have come down, and also the quality of ferro-silicon what they produce is, we talk about 65 and 70 grade ferro-silicon only.
Okay. Great.
And the fumes what you get, basically, if you see this ASTM or something, it says silicon metal or 75 grade ferrosilicon.
Okay. Okay.
Because the silicon percentage, if it comes down in the metal, your quality of the fume also will fall down.
Okay. Okay.
This whatever ferrosilicon plants, if they collect whatever 65, 70 grade what they are producing, my silicon dioxide will be in the range of 76, 78%.
Yeah, I started my research, Silica Fume, I got from Polgad, but now results are not received anything.
I know.
You know that after getting your from Welcome Norway,
Yeah.
then only some favorable results.
No. In fact, the silicon dioxide content is purity is less, and even the collection. Probably these plants do not have the collection facility also.
Okay. Okay. Yeah. And also, you mentioned the specific surface of these fine particles. Any instrument?
For BET, it is done by nitrogen absorption actually. Okay. BET, what we call.
The size what you mentioned also measured with that instrument only?
No. Yes. No, site by BET, they don't. They don't
0.1 micron. What is the name of the instrument? At least for the participant, they should know how it is.
it's basically what you do is BET, nitrogen absorption, where in this inert nitrogen atmosphere you will pick particle by particle. Particle by particle. Yes, and then read the specific set.
Okay.
That's how it is. It's done with the nitrogen absorption. Actually. In fact, I think specific surface area today, NCCBM Ballabgarh had, and NPL laboratory in Delhi had. And since once you open the nitrogen cylinder, you need enough samples to test. Otherwise, it becomes very expensive for them to test one single sample. The problem was that, but now I found chemical engineering department in IIT Delhi. I have married them now. I keep because in the lab it's readily available. I know one. I think you know Mr. Maiti sir. Maiti sir, Hasbi sir, udhar jao. Bolte he referred me some 8 years ago. So, I'm in coordination with them and getting updated reports.
You are Center of Excellence in Silica Fume there only.
Yeah.
Because the Delhi IIT campus have a flash mission center also, I know.
Mission also. I think Bhattacharya sir did a lot of things there.
Okay. Just to share information, there is one more speaker, I think VSVesvaraya, you know. He's an expert in production of international cement consultant actually.
Okay.
He's a consultant for all Lafarge also.
Okay.
The same thing, his additives are added during the grinding process to make a special cements.
Cement, yeah.
Just I'll share those talk next.
Okay, he is. When is that?
He's from Bangalore only. He was ACC, the plant head. The production was going in cement.
Okay.
Virada from North, I think.
Yeah. No, but when is
lecture? I will share that. Sir. Actually, till time is there. Sir, as 1 to 20 will be in abroad. After 21 will reach India. Therefore, I scheduled 27 something in that range. I will share those things. Sir. There's an interesting picture. If you can give some input to Silica Fume also added in that.
Input.
Yeah.
I'll put Virada sir to put Silica Fume.
Now, any questions, Sanat? Any questions from chat?
There are some questions. One is from Deepak Gurudev.
Okay.
Sir, can we use slag sand and silica fumes blended concrete? If yes, what could be the best combination?
No, I think you said slag and slag sand.
Yeah.
Slag and
both are same.
Yeah, both are same. Yes, I think it's a ternary blend. OPC, slag, and silica fume. Yes, I think you can use. There are a lot of projects which I've been using. I showed you the LNG tank project, Gujarat, Dahej.
What would be the best combination? His question is, what would be the best combination?
Best combination, I think I would go for say around between 45 and 50% of GGPS and similar quantity of OPC and 5% silica.
Okay.
Because instead of 8%, I say 5% because it's 3%, additional 3%. My GGPS will take care of it at a later age.
Okay. Because microfiller, you're using GGPS.
Yes. Yeah.
Okay.
Pragyan.
Just go.
Pragyan, you can ask the question directly.
She is muted, sir. You can just take the question.
Yeah.
Because what is the question?
Okay.
I think they are muted.
My question is, what will happen if we add in concrete mixture first cement and later silica fume?
Mixing sequence.
Okay. Basically, I think nothing will happen technically. The reason why I asked silica fume to be added first is it is in a densified form. Give enough time for it to be broken. Those agglomerates to be broken and bring it to its original form. Okay. That's how I said add it in the beginning. Okay. But one thing, since your question is there, I'll tell you. Always ensure you're adding admixture, chemical admixture, when cement is there in the mix. For example, if you're having silica fume, add admixture. This admixture, because of the surface action, it binds the silica fume. It doesn't allow it to disperse. The zeta potential, what we call. Okay. So when cement is there, cement is tighter with that. It starts behaving with the cement and silica fume will have the permission or the time to disperse. Okay. So ensure cement is in the mix when you're adding admixture. Silica fume is always there. Add cement and then admixture. If you see my sequence, it's that way only. But I'm trying to bring, you can add with cement also. I'm trying to bring silica fume earlier because the more time you give, the better will be the dispersion.
Yeah, mixing time increases, performance also increases.
Yeah.
Yes, next question.
No more questions, sir.
Yeah. See, if there is no questions, so actually we can conclude.
And this is not the end of the road. I think you must have noted down my contacts. You can disturb me anytime if you get any questions later.
I request all the engineers. I will share his details also in everything in our group. Please contact him for any troubleshooting required or any new material.
And sir, I think I would request you to send your rather share your complete postal address.
Okay.
I will send you a stick pen drive.
Okay.
It's a library of silica fume.
Hello, sir.
Yeah.
How a silica fume affect a compressive strength, sir?
Please introduce yourself. Please introduce the participant. I request. Please introduce and ask the questions.
Sir, I am Bijan Sri Maika, CMTI.
Yeah.
Advanced construction batch. Now this time I am in Pune, Maharashtra.
Okay.
What is your question?
I want to know how silica fume affect of compressive strength.
It will increase the compressive strength.
Okay, sir.
Basically, silica fume, what it does, it physically it fills in all the pores of the concrete. It makes the concrete dense. And it reacts with all this calcium hydroxide, which is a fluffy material, to give a good gel or good bond. And it makes it very compact, dense, and cohesive. And
yes, sir.
As a result of which the compressive strength increases.
Yes.
Okay, thank you, sir.
Thank you.
And impermeable also.
Yeah, impermeable. Yeah.
So wherever the durability is required, you have to make an impermeable concrete. Without this metal, you cannot do it. Therefore, you have to see any design of water storage structure, especially hydraulic structures, water storage structures, gas and oil structures, and where the abrasion is required, highly resistant abrasion, erosion. You have to think of only this material. You don't go, because sir also mentioned without maintenance. So maintenance-free concrete.
Maintenance-free. All repairs are always expensive.
Maintenance-free concrete, even though there is a cost is same. Only thing is you have to take care of proper mix proportioning, because you cannot use always some methodology and do the mix and finally take some percentage. Therefore, you have to do laboratory studies, trial mixes, make a very good mix design. Then this metal will give a life cycle cost. If you compare, it is less than conventional concrete. What I hope, sir?
Yeah.
Thank you, sir. Thank you very much. You are
Thank you, sir.
Yeah.
I tried high volume fly ash concrete with 50% of replacement with fly ash, sir. But in that case, we have collected fly ash from the 5th and 6th, this one, sir, actually. Hoppers.
Okay. You mean to say
finest was less than 40 microns in that case.
Okay, you mean to say ultra fine fly ash sort of. Yeah.
Yes, sir. Yes, sir.
Yeah.
But it is very difficult to get saccharate fly ash from the hopper.
Exactly. I know that one. Yes.
It will come in the mixed condition. It will come.
Yeah.
So one thing is the particle size, and next is the chemical composition of SiO2.
Yeah.
The silica fume particles will target, I think, 95% range.
Chemistry of the material.
Yeah, chemistry of the metal is very, very important. Where you want to make use, just chemical properties you have to check. not simply getting something and replacing.
And fineness is directly linked to this one, sir. Chemical reaction. This one. If it is more fineness and chemical reaction process will be more.
It will be more reactive sort of a thing.
More reactive.
Yeah, more finer, more specific surface area what you have or reaction to happen. Yeah.
I request all the participants to fill the Google forms for anybody interested for certification and attendance for the Nirmiti Kendra engineers. Thank you, Sanat Kumar, for sharing the feedback forms. Thank you, Siddappa sir, for your valuable time and very good information you have shared. At least think of silica fume material is there, and it will be highly useful where the abrasion, erosion, and also durability, and where I want to control the permeability of the concrete, the need of the material. And I think all Nirmiti Kendra engineers, this is one of the construction management upskilling also makes the selection of materials. See, that is the reason the silica fume, one topic we have introduced in online. The high-end speakers are able to come online and give the important lectures required in order to make use of this material whenever you come across any complicated mixed design required. I think you can, I'll share the contact number also. I will share the participant details also here. You can share your material from the company profiles, anything, everything.
Yeah.
It is useful for them. Thank you once again, Siddappa sir, and also thanks, our director for his presence, and also all the participants from CMTI and Nirmiti Kendra engineers. Last but not least, Mr. Sanat Kumar, you are the supporter of online. Hope today there's a NAC visit is there in CET. He is able to manage both.
No, he has been the backbone for
I told you now. Therefore, thank you very much, Sanat. I think you are there.
Yeah, Sanatji, thanks a lot.
Yeah, because he came 3:30 itself. Thank you. I think our visit is over. Visit is over.
Sir, meeting is over, sir.
Meeting is over. Visit. People are there in the campus.
Yes, sir.
Yeah.
Still they are there in the campus. Up to 8 o'clock, they might be there, sir.
Okay. Therefore, we will close the meeting. No issue.
Okay.
And I will request all the participants share the details through email, and I will forward to the speaker. Thank you.
Okay. Thanks a lot, sir.
Bye. Yeah. Thank you very much once again.
Yeah. Thank you.
Bye.
Bye. Bye.
Bye.
Thank you.